Hello, everyone. My name is Abdullah Ahmed, and I'm representing my troubled country, Sudan, in this space. So, on Sobol sampling. So, we start by why we need Sobol sampling is to evaluate integrations. Maybe everyone here in the room knows. So, evaluate integrals by summation, replace the integration by summation. And if the samples used for summation are well chosen or not random, it's called quasi Monte Carlo. And in quasi Monte Carlo, maybe Sobol sequence is the best, arguably is the best, because it scales with dimension and it uses GF2 operations or multiplication, so it's very straightforward. So every dimension of a sample or every component of a sample is computed by multiplying or reordering a van der Kolbos sequence, a bit reverse sequence. So reordering it by multiplying from the bit vector from the left by a matrix, a binary matrix. And all the operations are GF2, Galois feed 2, so this translates to XOR bit operations, so it's extremely fast. And also it has the best numeric integration from this, or almost the best, or effectively the best. And the point is that it's extremely fast, much faster than non-alternatives, and this like hides the fact that it can be faster, which we show in this paper. So you have matrices like this. These are binary matrices. The black dot is 1 and the gray dot is 0. So you multiply, you have a bit vector representing a bit reversed sequence number on the right. On the right, yes. And you multiply by this matrix. So the identity matrix gives you the x dimension or the phase dimension, the y, the Pascal matrix, which is like a Semitic triangle, and these are 32 bits. So this is the most common example. So for a generic implementation of this matrix vector multiplication, you would, for each dimension, you would choose the bit of the sequence number, and if it's set, if it's 1, you just XOR the column of the matrix. So it's very simple. And this is fairly fast, but this is not the best or the fastest way. For the first 2 dimensions, so the Sobol sequence is made of many dimensions. The first 2 dimensions are generated by the identity matrix and the Pascal matrix, and multiplied by a bit reversed vector. And it's used exclusively for at least two samplers in PPRT. So some sampling strategies only use 2D. So you don't go to high dimension. And this is why the first 2D are very important. And for the state-of-the-art implementation, of the current implementation, they use loopless bit reversal for the first dimension. You may wonder why are we using bit reversal? It's the identity matrix, but the vector itself is bit reversal. So they implement the bit reversal like that. In Hacker's Delight, you might find many examples like this. So no loop, it's just an operation of leaving the bits. And for the other dimension, the Pascal matrix dimension, they don't store the Pascal matrix. They just compute it using a recurrent. So it's compact. For the second dimension, it's compact, but it's not very fast. It's not the fastest like the first dimension. Another strategy, sampling strategy, using the high dimensional Sobol. So the first 2 dimensions are not that important in that strategy. So it works like this. You generate a global Sobol sequence for the whole scene, for everything, and consider the first 2 dimensions as if they are the image. So for this goal, you need to query the sample index. So you have a pixel, you compute a pixel by pixel, and you need to give the pixel coordinates and the subpixel sample index, and then you need to query the sample, the global sample index, so that you can retrieve it. So this means that you need to invert the first two dimensions, even though the first two dimensions are not very dominant, but inversion is very dominant. And the state-of-the-art implementation of inversion is rather slow, and it involves also lookup tables. So this is also known in or published in the literature. This is a paper we published last Graph Asia about if you have a Hammersley sequence, a Hammersley net, for example, or gray code net, or any favorable net, LP net, you can convert it to a sequence like this using these drivers. So this rely on some properties. For example, that any matrix that can be combined with the J matrix can be factored into LU or decomposed into LU decomposition. So all these are backgrounds, and now starts our work in this paper is to speed up from order m, number of bits, to order log m. How can we do that? So it starts with a very simple observation that the Pascal matrix is self-similar. So parts of the matrix resemble each other. It's a Sierpinski triangle, so the typical self-similar. If you shift the matrix, I wished I could animate this, but if you shift the matrix by 16 steps to the right, it perfectly overlaps with itself. And if you make any power of 2 shift, also you have good overlaps like this, but not very perfect overlaps. But if you combine the shifting by masking, if you mask first some columns and then make the shift, you would have perfect overlaps like this. And what's the essence of this shifting is that if you shift and then add the matrix to itself, the shifted matrix to the original matrix, you will wipe or remove some of the bits. So if you shift by 16, you will remove the top triangle. If you shift by 8, you would remove a few triangles and so on. And the shifts effectively correspond to multiplying by a matrix like this. A similarly shifted matrix would make the shift. So if you multiply by this matrix, you would shift by 16 and so on. And how that would translate into coding, shifting of the matrix is equivalent. So if you shift and multiply by the vector, it's equivalent to bit shifting the vector itself. And if you mask columns from the matrix, it's equivalent to masking bits from the bit vector. So it translates to very simple operations like this. So if you do that, you end up with this very simple, very compact code for the Pascal matrix. Multiplying by the Pascal matrix, you phase shift by 16, you mask and shift by 8, you mask and shift by 4, you mask and shift by 2, and so on. So it reduces to these 5 steps. So this is the first Goldman. And from this we learn like a concept, a new concept, diagonal, I call it diagonal matrix factor. So if you can factor any binary matrix by diagonally running matrices, then you can achieve this performance improvements. So for the inversion matrix, we need to do the same because it's a real bottleneck in the inversion, not like the generation. So for the inversion, you need to generate Morton code for the pixel coordinates, and you can do that by concatenating the identity matrix for the first dimension and the Pascal matrix for the second dimension. What does this compute? It actually computes, so the inverse matrix would precisely compute the sample index of the, if you have a 16K, 16-bit resolution of the image, and you pick up for each pixel the sample in the bottom left corner of each pixel. This would give you the index of that pixel. So inversion is not straightforward as generation. So we had to do it in 3 steps, explained in the paper. But eventually we reduced it to diagonal matrix factoring, and we managed to implement it like that. Just looking back, this is straightforward to factor because it has the Pascal. Remove the lower triangle and then factor is similar to the previous. So this is the resulting code. The third for so IP invert, XU, OXZ, U inverse, all these are using matrix factoring, diagonal matrix factoring. So 3 steps. And this is the results that we managed to obtain. Extra results that we managed to obtain is that this is the original Sobol. It looks like that. Even visually, it's evident that these are better distributions. And in theory, like using the last year paper, the segregation paper, you can reorder the Sobol into this, or into this distribution. But the implementation is open. It's not straightforward. And the problem is that you use a very different matrix or a different matrix for each resolution. So we managed, after some play arounds or some analysis, we managed to implement it using the same diagonal matrix factoring, and in one implementation, one generic implementation, we managed to obtain all these variants. So this one, the last one here, has provably the maximum possible spacing between the samples. It wasn't invented by us, it was by Keller too, Grunfus and Keller. So this is the weighted for results or comparison. This is the standard implementation from PPRT. The rate is 59 million samples per second. This is fairly fast for all rendering purposes, but we managed to bring it to 340, so 5 times faster. It's already very fast, but we made it 5 times faster. You may ask, who cares? But it matters that we managed to implement the improved version twice as fast. This is what makes the difference. And these are just for comparison, like the Helmer method and the gray code, the scanning order. The problem with this is that they cannot be used with random access to samples. You cannot just query any sample and retrieve it. So it doesn't work for global samples. And it's also not flexible enough to integrate the improvements there. So this is the main result here. And these are the conclusions from this exercise, that it's fast, provably fast, or objectively provably fast, because the order is faster. And if we can look here, it's almost 6 times fast, 5 times faster. This is precisely the ratio between log, or roughly the ratio between log m and n. So 32 bits and 5 steps. 32 steps versus 5 steps. Roughly, yeah, it's almost 6 times. Yeah, roughly the same ratio. So it's objectively fast, objectively compact, because we don't have any lookup tables for inversion. So just a few lines of code and that's. And it's elegant. This is subjective, but I believe it's elegant. For me, at least, I like it, but I don't know. I hope you like it. Diagonal, we learned that diagonal in general, more generally, is diagonal matrix factoring, like reduces the complexity to log m, and then it pays. And all the costs that we had to pay, because the implementation is that, all the costs that we had to pay is a deep understanding of the matrices. So learning about the actual elements used in your code pays. And we learned that fast doesn't mean the fastest. So even if it's very fast, there can be a chance that it can be fast. And we learned that speed performance admits quality improvement. So even if it's already very fast, make it faster to make it better. So this is what we did. So thank you. That's